কিনেছিলাম
Uh,
তো।
in the introduction, let me tell about what are the applications of mathematics that existed in Bharatvarsha,
মুছতে হতো তো।
in ancient India. When I say Bharatvarsha, I mean ancient India, which extended on the north from Himalayas to the south, to the in the south to the sea, Arabian Sea and or Indian Ocean, and in the east from Afghanistan, in the west, sorry, in the west from Afghanistan, in the east to Indonesia. So the ancient India. In that part, early days, we used mathematics for enumeration or counting by using numerals, arithmetic, etc., for which we will find references in Rig Veda. Rig Veda talks about numbers. We'll see it powers of 10. These are parts of Vedanta Jyotish. Then for different modeling, we use mathematics like trigonometry, approximations, equation solving. This we can find out in Surya Siddhanta and later in Aryabhatiya. Then in commerce, India was very prosperous because of commerce. In commerce, we find mathematics in arithmetic, algebra, equation solving, etc. That you can find out in Arthashastra, Kautilya's Arthashastra, and the Bakshali manuscript that we'll discuss today, if time permits. And then in architectures, this used geometry, particularly right angle triangle, circle, pi, square root, etc. That we'll find out in Silva Sutra, and that we'll discuss today. Then some advanced modeling, like function approximation, polynomial series, infinity series, etc. That we find in the works of Pingala, Madhava, in Yuktivasa, in the Madhava's school or Kerala school. Then Newton Leibniz, why I call Newton Leibniz, say it Newton Leibniz here, that we'll see later today. Then Ramanujan, that also we'll see in the next lecture, in the Monday lecture. Next. Now let us divide the period into pre-Vedic period or Sindhu Saraswati period, Sindhu Saraswati civilization period, then Vedic period, then post-Vedic period, and modern period. In the pre-Vedic period, if we call it pre-Vedic, we don't know whether Veda was existing in this period, in this Sindhu Saraswati civilization period, because the script was different. Language may be same, may not be same, we don't know. But the script was same, and there was a civilization that we from the excavation, we see these pictures. If you see the pictures, in the top picture, you can see the squares, arrangement in square or arrangement in rectangle form. In the bottom picture, you can see a circle. There is a well which is circle, a circular. So circular shapes were known to them. These square rectangular shapes were known to them, to the Harappan civilization. Then they used bricks. These bricks were in the ratio of 4 is to 2 is to 1. Each brick was in the ratio of 4 is to 2 is to 1. And the in the top right, you see the weights. They used weights for measurement. So those weights are there. They are also in a particular proportion. That we know today. Then next. Uh, Then we saw there also we found in different parts, including the Sindhu Saraswati civilization place excavation. We found the measuring scale, linear scale, or length measuring scale. That we see. These are the length measuring scale. Now, what do you infer from this? We infer two, three things. One is those people in those era they knew about geometry definitely because of the shapes that we find out that they knew about geometry. Then because they were using measurement. There are measurements, so they must be aware of some numbers, a number system. Whether it is decimal number system or not, we don't know. But there was a number system, definitely there was a number system. So two things were existing even in the uh, Indus Valley or in this Sindhu Saraswati civilization period. Geometry, people were aware about geometry, people were aware about number, and if they were aware about number, they also knew definitely some amount of arithmetic, because with number what one will do. So they must be adding, subtracting, that much must be there. So this much we know, or we infer from this Hindu Saraswati civilization, that ancient India in the ancient period, which is the period that we know, which is the most late part in the or the past that we go up to that period. If we go up to that period, we know that this was there, number was there. Okay, but we say that decimal number or numbers came to India later. People say that, but I don't believe this because of this. Next. Then you see in Rajasthan, Kalimbagan, these excavation, these are dated to 2600 BCE to 1900 BCE, before the current era or before the Christian era. This is the period where you see the tiles. These tiles contain a particular geometry, a type of particular geometry, carved in geometry. This geometry is you can see circle, and using circle they have generated this geometry. And how it is generated, these curves are described by a point P on a circle of radius a by 4. If from the figure you can see what is a, so larger circle is a, so its radius is a. So take a by 4 and P on a point on a circle, and roll it on the inside of the circle of radius A. Total arc length will be 6A. This is later described, this geometry is later described in the Bodhayana Sulva Sutra. We'll see what is Sulva Sutra later in the first chapter. Next. Now that is pre-Vedic period. Then if we say that pre-Vedic period didn't continue into the Vedic age is a different period. Then in the Vedic age, we look at the Vedas. These are some verses from the Vedas. The first verse talks about 200,000, 200 million, or 100 trillion. Second verse talks about the numbers 1, 3, 5, 7, etc. up to 33. Then numbers 4, 8, 12, 16 up to 48. Now there are two separate groups of numbers. If you look at these two groups of numbers, one group is odd, other group is even, which means they had knowledge of even number and odd number in those days. That is clear from this. Next. Then only did they know 10 or 100, 100,000, 100 million? No. They also knew 20, 30, 40, etc. In from the Rigveda, you can find out those numbers. Give me a minute. Let me take some water. Again, in Rigveda, there is a shloka which describes 3339 as sum of 33 plus 303 plus 3003. Now, if you look at this, we can say that this is something like a place value system, decimal number place value system. And this is close to 18 years, which is the period of eclipse cycle. So this is something like a decimal system. So in the Rigveda period, maybe they knew what is decimal system, but it is not, decimal system is not documented. That we can say the details of decimal system was not documented or is not available in Vedas or other books. There might have been other books, we don't know. But this was there. This number, when you divide 33, the 3339 into this part, this indicates that there was knowledge of decimal system. Similarly, we had knowledge of zero and infinity. This is from the last sloka, Purnamada Purnamidam. That sloka gives you the knowledge of infinity and zero, which means if you take out anything from zero, you will get zero. Take out zero from zero, you will get zero. Add zero to zero, you will get zero. Take out anything from infinity, you will get infinity. Add anything to infinity, you will get infinity. Zero and infinity are complementary to each other, and they are the beginning and end of the universe. Next. Then there is a shloka in Agni Puja. For Agni Puja in the Yajurveda, this shloka tells about 110, then 100, and then 1000, etc. 110, 100, 1000, that is described in this shloka. So this is uh, purely indicating a decimal system. Next. Then, if you come after the Vedic period, the next period is Ramayana period. In the Ramayana period, you see the quantification of army, it is 1 koti to 1 Mahayuga. So these are in numbers of 10. So 10 to the power uh, something. Uh, Next. In Yuddhakanda, this is described. Then after this period, the Ramayana period, you come to Mahabharata period. The army is described in the Mahabharata, as well as Mahabharata. The numbers you can see, once you see these numbers, one will be sure that people knew about counting and numbers. And that is the counting and numbers were based on decimal number system, definitely. Next. Then this is the largest number that we come across in different books in those time, 10 to the power 53 or 10 to the power 140. These were the largest number that we came across. Next. Then in the Vedas, Rig Veda and Yajur Veda, this rule of three is also described in a shloka. What is rule of three? Today it is very simple, but for those days, this was something like an invention. If you have an equation of the form a by b is equal to c by x, then we can find out x as bc by a. So you can evaluate x if you know a, b, and c. This is a iterative process. Why they used it? To predict the motion or as a linear model, predict the motion of planets as a linear model. For example, suppose a planet moves delta s units in time delta t, then over a period of time t, capital T, what will the movement, how much it will move? If it moves st amount, then st is equal to delta s by delta t into capital T. Now delta s by delta t is small amount, capital T is the larger amount in time. Now, delta S by delta T, so it reminds us of calculus that we are using here today, or differential calculus. They never use differential calculus in the form that we are using today, but the form you can see here. This is available in Bodhayana. Next. Now, Veda that was discussed up to now uh, in all these, that has two parts. One is philosophical parts or para part. Other is knowledge part, which is apara. Apara has four Vedas. It contains four Vedas, and each Veda has six parts: Sikhya, Kalpa, Vyakarana, Nirukta, Chanda, and Jyotisha. We'll discuss today about maybe Kalpa Chanda and something about Jyotisha we'll not discuss in the next lecture. So Chanda Kalpa we'll discuss. We'll start with Chanda. So Chanda means Chanda Shastra. That is prosody. In English, we call it prosody. This was encoded into the form of a book by Maharshi Pingal. And in that book, there are 8 chapters. The eighth chapter gives 6 combinatorial algorithms: Prastara, Laghupriya, Sankhya, Nashtam, Adhya Yoga, Uddetanas. We'll see some of these algorithms today. And I remember one thing that this Chanda Shastra, he has compiled it. Most of these is compiled, which means the knowledge was pre-existing and he has compiled the pre-existing knowledge with his own contribution. He has added his own contribution, but compiled is the pre-existing knowledge. Next. So let us start with the algorithms. First algorithm is Prostara. This gives you a procedure to lay out all possible metrical patterns with a given number of syllables as an array. So if you arrange syllables, a number of syllables is given to us. If we are going to arrange the syllables in the form of an array, then how many metrical patterns will be possible? So that is what is Prostar. Now, to do this, he says that there are 2 types of syllables. One is called Guru syllable, other is called Laghu syllable. Now, Guru syllable is usually the conjurance. Laghu syllable is usually the conjurance, and Guru syllable are the vowels or consonants in conjoint with vowels. Usually, this is what it is. Next. Now, if you have these two, Guru and Laghu, then the second algorithm says mix them themselves. So first you take Guru and Laghu, then take Guru and Laghu, then mix them themselves. So take Guru and Laghu. So Guru Guru is Guru Guru, Laghu Guru is Laghu Guru. Then in this bottom one, Guru Laghu, so Guru Laghu, Laghu Laghu, Laghu Laghu. So now you have got Guru Guru, Laghu Guru, Guru Laghu, Laghu Laghu. Now next, mix them themselves again. So you have got this one, Guru Guru Laghu Guru, and Guru Laghu Laghu Laghu. Take that 2 times because there are two patterns. So take them 2 times. Then mix them themselves again means mix them with Guru and Laghu. So we will get this pattern. Now next, if we look at that pattern and we will put G is equal to 0, Guru is, we take, if you take Guru is equal to 0, Laghu is equal to 1, then on the left hand side, the first row is Guru Guru, all Guru, and the 8th row is all Laghu on the left hand side. That is equivalent to in terms of if you put Guru is equal to 0, Laghu is equal to 0. Remember that Pingala has not said that Guru take Guru is equal to 0, Laghu is equal to 0. That is what we are saying. I am saying that Guru is equal to 0, Laghu is equal to 0. In today, when we are analyzing that, we are saying this. So that it becomes 0, 0, 0 to 1, 1, 1. And if you take a mirror reflection of that, that gives us 0, 0, 0 to 1, 1, 1. But it is just a mirror reflection. So these numbers represent 0 to 7. In the binary system, this represents 0 to 7. So a mirror reflection of the uh, prosody or of the metrical terms gives us a binary equivalent. So binary, you can match it with the binary number system that we study today in the digital electronics. Next. Then I will see about a rule of Prostar, how to get this Laghu and Guru. So what we will do is start with a row containing G. So we have LLLG, LLG, so it contains a G. First, identify G from the left. So from the left, we see the third one from the left is G. Next, place L below the G. So below G, we'll place L. Bring down elements to its right without change. Now here to its right, there is no element. So we'll not bring down anything. But, and we are writing L below G. Next, fill all places to its left with G. So these two will be G. Now from left again see whether where is the G. G is in the first position. So we'll bring L below it. Then bring down all elements. After that on the right hand side there, left hand side is there is nothing. Third, fourth row, G is in the second position. Bring L. Then on the right hand side L is there. Bring down. Left hand side will be G. So this way, if we continue, this fifth position will get all L. So continue till the row of L is created. All L is created. So this is how we can create a Prastara rule. Next. Then Sankhya. This is a process of finding the total number of metrical patterns in a row. Instead of going through the algorithm, let me try to explain the algorithm in terms of an example. Suppose we have a 6 syllable meter. So a number of syllables is 6. N is equal to 6. What we will do is we will divide n by 2. So divide 6 by 2. If it is divisible, then write what is the quotient and mark 2. Then divide the quotient by 2. If the quotient cannot be divided by 2, then subtract 1 from the quotient. So 3 cannot be divided, so subtract 1. So 3 minus 1 is 2. When you are subtracting 1, mark 0. So in the first step, we had marked 2. Second step, we mark 0. Now, what is the quotient? It is 2. Divide 2 by 2. So that gives us 1. So since it is divisible by 2, we will mark 2. Then 1 is not divisible by 2. Therefore, we subtract 1 from 1. So that gives us 0. Since we have subtracted, we mark 0. And so we have generated a sequence which is 2, 0, 2, 0. Now, once you generated that sequence, then start with the number 1. N is equal to 1. Start with some number q. Q is equal to 1. Let us take q is equal to 1. Then read 0. The first number is 0. The last number is 0. So you read 0. On the right hand side, last number is 0. Read 0. Multiply this q, or which we took as 1, by 2. So 1 into 2. When you are reading 0, multiplication by 2. So 1 into 2 is equal to 2. Now q becomes 2. Then second is 2. Read 2. When you read 2 instead of 0, then square the number q. So 2 will be squared, it will be 2 square. Then 0. So q is equal to 2 square. 0 is, once you encounter 0, multiply by 2. So 2 square multiplied by 2, that gives us 2q. Then read 2, last number is 2. When you read 2, multiply, square it. So 2 to the power 3 will be squared. That gives us 64, which is 2 to the power 6. So from this, what we get to know is, if we are given a system or n syllables, then n syllables can form 2 to the power n words. Because syllables can be divided into two groups, Laghu and Guru, therefore n syllables can give us 2 to the power n words. Next. Then let us process find the process of obtaining the total number of metrical patterns in a given row. So suppose the row number is given, or a row is given, what will be the number of sutras? So this sutra gives us uh, Suppose, okay, this SR is the sum of all sankhya's, all numbers. Sankhya means numbers. It is the sum of all numbers for R is equal to 1, 2, 3, 4, etc. Then this Rocco says if you have R is equal to up to n, then S1 to Sn if you add, that will give us 2Sn minus 1. Next. The next Roko says Paripurnam that says Sn plus 1 is equal to 2Sn. Now, if you use these two slopes, next, they imply that Sn is equal to 2 to the power n, as we have got earlier. And uh, 1 plus 2 square up to 2 to the power n is equal to 2 to the power n plus 1 minus 1. This is a geometrical series. So it gives us a formula for geometrical series. Next. And next. Then the Nosta is for any given row number, find the corresponding metrical pattern in the Prasthana. This also I will explain in terms of an example. Find the seventh metrical form in a four-syllable Prasthana. So there are four syllables. We have to find out what will the metrical form in the seventh row. What we will do in the Prasthana, first take the row number. In the row number, if the row number is possible divisible by 2, divide it by 2 and write L. If it is not possible to divide by 2, then add 1 to it and divide by 2, then write G. So 7 is not divisible by 2, so 7 plus 1 by 2 is 4. We are writing G. Now 4 is divisible by 2, so 4 by 2 is equal to 2. Since it is divisible by 2, so we'll write L after G. So GL. Then 2 is also divisible by 2, giving on 1. So therefore we'll again write L. So GLL. Then 1 is not divisible by 2, so we add 1 to 1. So that becomes 2. 2 by 2 is equal to 1. Therefore we'll write GLLG. Now there are four syllables. We have got four number of four LG. Total is four GLLG. So that is four. So four syllables we have got. Now, if we set G is equal to 0 and L is equal to 1, we immediately see that this Nosta process leads to the desired metric form by the binary expansion. Now that is seventh metrical form, so you can see whether it is 7 or not. Take 7, then we had for G is equal to 0, you put 0, 0 into 2 to the power 0 plus 1 into 2 to the power 1 plus 1 into 2 to the power 2 plus 0 into 2 to the power 3. So that gives us 7 plus 1. And next. Then next algorithm is called the Uddishta algorithm. In this, we find the row number for a given meter. If a meter is given, then we'll find out the row number. What we will do is, we start with 1, then skip the G and go to L uh, to find out the row number. So we'll scan the pattern from the right, beginning with the first L. So here it is given G, L, L, G. So skip the G, go to the L. From the right we are coming, in the rightmost is G. So skip that, go to L. So once you go to L, you get 1 into 2. You have started with 1, multiply that by 2. So 1 into 2. Then we find another L. So we get 2 into 2, that is 4. Finally, we get another G. Last we get G. So once we get G, then we will double it. So 4 will be doubled, then 1 will be subtracted. So 4 into 2 minus 1. That gives us 7. So that is means the seventh row. Next. Then this is another method of finding the row number also from the same procedure. So this is another method. I am not going to discuss this. Uh, if you, I have provided the handouts. If you read it, the handout, you will understand it easily. Next. Now, up to now, what we have seen is the binary system, equivalent of binary system in ancient India given by Pingala. But we acknowledge Leibniz as the father of calculus and father of binary number system. There is, but Leibniz acknowledges Madhava, Indians' influence, particularly Madhava in his work, but he never mentions Pingala. Similarly, Pingala also gives us the Fibonacci series that we'll see just now. So the credit for binary system, some credit for binary system should have been attributed to Pingala also, but it is not there. All the credit goes to Leibniz. Next. Then the Lagakriya, which says for a Purnamiti. It is a very brief sutra unless one explains this. Halayudha has explained it clearly. Then it is difficult to understand what is mentioned there. In this, we find out the number of metrical forms for a log for no, for a number of lagus or gurus. I will give you an example. You will understand it next. So the algorithm is like this. Its first stage cell will be filled with number one. So topmost cell is filled with number one. The two cells before that, after that, the twin cells, they will be filled with number one. In the third row, the first cell and last cell will be filled with number one. The middle cell will be the number which is the sum of the numbers above its adjoining cell. So so middle cell above that, the adjoining cells are 1 and 1. So they are added, that gives us 2. Then if you go to the for this way, it will continue. Now go to the fourth cell. In the fourth cell, the first cell and last cell will always be 1. Uh, As you expand it, first cell, last cell will always be 1. Then the second cell above that is 1 and 2. So that is 3. Third cell above that is 2 and 1. So that is 3. So this way you can expand it. This is the Lagakriya. Next. And this is called the Meru Prasthar. It looks like a Meru. Meru means it looks like a hill. So as if a hill is expanding from its top to bottom, it is expanding and with the numbers. That is why it is called. And what does it signify? It gives the binomial coefficients. So first two cells leave it out. Or you can say x plus y to the power 0. First topmost is x plus y to the power 0 is 1. So that is 1. X plus y to the power 1 is x plus y. So coefficients are 1. Third cell, if you come to row number 2, R2, then x plus y square is equal to 1x square plus 2xy plus 1y square. Look at the R2 row. It is 1, 2, 1. Those are the binomial coefficient. Look at the R3. Those are the binomial coefficient for x plus y to the power q. So this way, if you keep on increasing, if you go to the R6, you will get x plus y to the power 6. What will be the coefficients? Next. Now, what is the use? Suppose we have 6 points. In how many ways one can get 2 tails, or 5 tails, or 3 tails, or 2 heads? How to find that? That you can do you can get it from this Meru Prasthara. Next. So there are 6 coins. So go to the row number 6, R6. And in the R6, the first cell says that you will get 0 tails and 6 heads in one way. Then the second cell says that 1 tail, 5 heads in 6 ways. So the number that is there, 1, 6, 15, 20, 15, 6, and 1, they are saying us in how many ways you are going to find out. The first one is 0 tail, then 1 tail, 2 tail, 3 tail, 4 tail, 5 tail, 6 tail. So 0 tail means 6 head, 1 tail means 5 head, this way. So using this Meru Prastara, we can easily find out the combination. How we can find out the possible all possible combination. So this shows that combinatories was available in ancient India. Then there are two other slocos. Both these slocos give this formula Sn is equal to Sn minus 1 plus Sn minus 2. Now, if you use this formula, that generates the Fibonacci series. What we today know as Fibonacci series, these two slocos give us. Now, look at the period. One is 7th century current era, other is 1150 current era. Okay. Hemachandra gave it 1150 current era. Now, what is Fibonacci series that you know? If you take this Meru and add the corners, that gives us the Fibonacci series. If I add the corners, what I get? 1, 1, 2, 3, 5, 8, 13, etc. And these numbers are Fibonacci series numbers are in golden ratio. Next. Who gave this Fibonacci series? We know why it is famous as Fibonacci series because uh, Leonardo Fibonacci, he gave this series 1, 1, 2, 3, 5, 8, 13, that series he gave. But he was first to acknowledge the Indian way of mathematics and Hindu numeral systems in Europe. Now look at this, his period, 1170 to 1250. Harayuddha was 1150. So at least 20 years before Fibonacci, this series was known in India. Next. Now, this Meru Prasthana, that is also known as Pascal triangle. Pingala in India gave it around 200 BC before the current area. That went to Persia in the 11th century, went to China in the 13th century in a different form, then to Italy, and had to France in the 16th century. Now, if you look at this, this is actually this Varna Meru or the Meru that Pingala gave is actually a rotated version of the Pascal triangle that we know today. Next. So they are one and same. So that is one part. The second part is the Sulba Sutra or the rope principle that we call rope principle. These are the guiding principle for temple architecture, construction, sculpting, and many more. Different texts are available for this Shilpa Shastra, Manasara, etc. And using this, what we can do is we can get different geometrical shapes and transform one geometrical shape to another geometrical shape. This is a list of what we can do with it. There are many more beyond this. Next. Now, what is a sutra? Why it is called sutra? That is important. The sutra is Swalpakharam, which means minimum number of alphabets possible. Alphabets will be used. Then it should be Asigna Dhyana, which means unambiguous. There should not be any ambiguity in the sutra. Saravan, which means it should be concise. Then Vishwato Mukham, which means it must be universally true. Everywhere it should be true. The sutra should be true always. Astovam, there should not be any redundancy in this. No redundancy. Then it should not have any flaw. It should be without any flaw. If something has this character, then it is called a sutra. A sutra has these characters. So if you look at this, sutra is a concise form of expressing something. It does not include the proof. Like today, we all remember that the sum of two sides of a triangle is larger than the third side. That we know. But that is the sutra. That is the theorem or sutra, whatever it is, whatever you call. That is the sutra. But most of us may not remember the proof. But we are using it. The sutra is something like this. What you are going to use is the sutra. The proof is not available in the sutra. When the sutra is codified, the proof is not available because the proof is not useful for general public. General people will not use, common people who do not require the proof. They require what is only the sutra to use it. So they require the utility. Therefore, proofs are not given there. And in those days, the proofs were maybe available to the Sishyas. These were transmitted in the Suti Parampara from Guru to Sishya. So the proofs may be available to the Sishyas, not to everybody. And they have codified these sutras without the proof, which means we have lost the proof. But some of these proofs are now available. Later, these were made available in something called Yukti Vasa. That will come to later. There, the proofs are what we call the Pratyakha Praman or the empirical proof. But the logical proof may not be available there. We'll see some logical proofs in the today's context later. Next. Now, why they required these sutras? Because in those days, early days, they were performing some rituals. In the rituals, they have to construct some pedestals. And these pedestals are different shapes. And these shapes are fixed. For example, in the bottom, if you look at this, this is called a Sena city. This looks like a falcon or Sena. In Sanskrit, it is called Sena. So it looks like a falcon. Now, the city or this pedestal, it has 5 layers of bricks. In each layer, there will be 200 bricks, and total will be 1000 bricks. Size of each brick is specified. This will be the ratio of brick. What will be the size, whether it is square, whether it is rectangle, whether it is a triangle, irrespective of that, for each one, each possible type of shape, the size is fixed. Next. So the size is fixed. So accordingly, you have to generate this shitting. No two layers will be, no two consecutive layers. Like the odd layers will have a given pattern and the even layers will have a given pattern so that it will become stable. If all of them have the same pattern, then the pedestal will not be stable. It will break down or it will not be stable. It will blow up. Next. Now let us discuss about Sulba Sutra. It was given by different rishis at different times. The oldest maybe is the Bodhayana Sulba Sutra, which is more than 3000 years old. It has 3 chapters, 520 sutras. Then there is Manava Sulba Sutra, Apastama Sulba Sutra. These are important. And Maitrayana Sulba Sutra. Uh, uh, Ba- Badula Sulba Sutra is also important. Next. We'll consider some of these. Now, how it is used. In the Sulba Sutra, what they used is they used one nail and a rope. Using a rope and a nail, they used to rope and sanku or a pole, nail or pole. Pole, nail and a rope. So first is for find out the east-west direction, correct east-west direction. Find out the correct east-west direction. So what you will do is take a Shanku in the early morning, before the sunrise or after the sunset, take a Shanku, put it, which means take a pole, erect a pole, then take a sutra, which is a rope whose length is 2 times the length of the pole or more than 2 times the length of the pole. Then draw a circle taking that rope as the radius around the pole and watch the shadow of the pole in the early morning and in the afternoon. In the early morning, when the shadow crosses the circle, at the point of crossing, mark it as west, and in the evening, the point of crossing, mark it as east. So these are the two east-west directions. Join them, this gives you almost accurate east-west direction. Why this is done is because every day sun does not rise in the exact east direction or exact west, or does not set in the exact west direction because of the orientation of the earth and the precision of the earth's axis. So that is why it is not in the exact east and exact west direction. This, but using this method, we get the exact east and west direction. Next, then we have to draw a perpendicular bisector to this line, which is connecting the east-west direction. So what we'll do is we'll connect the east and west point. Take a rope whose size is more than the twice the east-west size. Draw a line east-west. Take a rope. What is the length of that rope is WE, and it should be twice the WE. The rope size should be twice the WE or more. Then take a nail. Then take three nails. Put one nail at east, one nail at west, and the other nail at the middle of the rope. Then draw it towards the north, and wherever it stretches completely, put it as north, mark it as north. Then draw it towards south, wherever it stretches completely, mark it as south. Connect those two points, north and south point, that gives us the perpendicular bisector. There is another method that will be clear later. Next. Now, why you do this? This is done when these yajnas are performed to uh, find out the exact east-west direction, uh, and then to construct those pedestals. And on the pedestals, there will be sacrificial fire. So, sacrificial fire, in those days, there were three types of fire, sacrificial fires. Tatagni, one is in a square, other is in a circle, other is in a semicircle. The beauty was all these three have the same area. So, first we have to construct a square. Once you find out the east-west direction, then construct a square whose sides are aligned to east-west, north-south. Next. The shloka gives us the procedure. I am describing the procedure instead of explaining the shloka. So stage one, we draw the east-west direction. So one line from east-west, both these red dots in the top one, they are east-west direction. So draw a line. Then draw a circle, taking this line as the diameter, draw a circle passing through those two dots. Then draw another circle, two circles, taking these two east-west points as their centers. And the diameter is EW, east-west. What you have, the radius is the diameter of this small circle at the stage 2. Radius of the large circle is the diameter of the small circle, stage 2 circle. Now, when these two large circles, wherever they cross, those points you mark, join those 2 points. That line gives us the perpendicular bisector of the east-west direction. Now, let us say that that line crosses this circle, smaller circle at two dots, the green dots. Now, what we will do is we have got four dots, two red dots, two green dots. Taking these four dots as the center, draw four more circles which are same of the same size as the blue circle shown at stage 2. So those circles will cross at these purple points. So we have got four purple points. Join those four purple points in the stage 5, you will get the square. So to get a square, we use this method. Next. Now, once we got a square, we have to transform the square into a circle whose area is same as the area of the square. So take this square, then and take its um, corner as the diameter of a circle. So draw in the stage 1, take the square. Stage 2, take the corner of the diameter of the circle. So draw the circle in the stage 2, and from center is O. From O, drop a perpendicular onto the side BC and extend it to meet the circle at point P. That is in the stage 3. Then in stage 4, what you will do is find out what is QP. Take one third of QP as QR. So from Q towards P, take one third of QP. That point R, that is the point R. Then draw a circle with O as the center and OR as the radius. Draw a circle. That circle has the same area as the area of the square. Next. Now from that we get something very interesting. Let us take this. Now, AB is the side of the square. So let us take AB. AB is equal to 2OQ. From this figure, you can find 2OQ. Let us take it as 2A. If the side of the area square is 2A, that is given. Then OR will be equal to R small r, which is to be determined. We have to find out the radius of the circle, which has the same area as the square. So OR is equal to R. Then OA, which is equal to OP, because it is the radius of the circle with perimeter, which is red circle. So OA is equal to OP, that is equal to root 2A. Why it is root 2A? Because side of the square is uh, 2A, therefore the corner, half the corner will be root 2A. Corner will be uh, 2A plus 2A, which is 2A square plus 2A square. So that will, from that, if you take the square root and divide it by 2, so that will give you root 2A. Then QP will be equal to OP minus OQ, that is root 2A minus A. If you take A common, it is root 2 minus 1. So we have got QP, we have got OA, etc. Now find out what is OR. OR is equal to the R, radius small r, that is equal to A, which is OQ. OQ is A plus 1 by 3 of QR, which is 1 by 3 of QP. Which is QR is 1 by 3 of QP. So A plus 1 by 3 of QP. Now QP value, we have got put there, this A value. So then you will get A by 3 into 2 plus root 2. Now interesting part here is it contains a term root 2. What is the value of root 2? That is given in Bodhayana Sulva Sutra in this formula in the form of a series. Root 2 is equal to, is approximately equal to 1 plus 1 by 3 plus 1 by 3 into 4 minus 1 by 3 into 4 into 34. You can extend that, but this gives you up to this. Then if you look at the Shoko, last is Sabishesa, which means after this there is something. This is approximation. So root 2 is approximated by this. This is 577 by 408, and we know it is 1.414. We use 1.414, but this is up to accurate up to this point. 686 up to that point, it is accurate. So root 2 value, accurate value, was given in Bodhayana Sulva Sutra, much before that came to us from the Europe. Next. Then, if you transform a square into circle, circle also can be transformed into a square. I will skip it because we don't have much time left. Now we have to cover something else next. And then comes the Pythagoras theorem, or popularly nowadays it is called Pythagorean theorem, because some people believe that it was not given by Pythagoras but by his students or followers who are called Pythagoreans. Therefore, this theorem is called Pythagorean theorem, which was given actually by Euclid. Now, whether it is Pythagoras theorem, if it is Pythagoras theorem, it is 500 BC, the period of Pythagoras. If it is by Euclid or if it is by Pythagorean theorem, it is 200 years after that, which means around 300 BC. It says that base square plus side square is equal to hypotenuse square for a right angled triangle. And that is what we know in the school. Now, next. Now, in Babylonian clay tablets, number Pipleton 322, this shows triplets which obey the Pythagoras principle. And these clay tablets were 1300 years before Pythagoras discovered the theorem. So Pythagoras was 570 BC to 490 BC. These were 800 BC, 1800 BC. So much before Pythagoras, these triplets were known in Babylon. Next. Similarly, in Egypt, these were also known 1500 BC, at 1500 BC. Next. Now let us come to India. In India, the Baudhayana Zulba Sutra, which is dated by the West to be around 800 to 400 BC. I don't agree to this dating. This Ashoka says that if you stretch a rope along the length of a diagonal, that will produce that. We say that means that area which the vertical and horizontal sides make together. So here you can see P and B are vertical and horizontal side. H is the diagonal. So the area of P and B is, if you add them, that will give the area of H. But in the Shoko, we don't find uh, the mention of square, and therefore we don't find the mention of area. So some people say that the Baudhayana Sulva Sutra may not be Baudhayana Sulva Sutra may not be giving the Pythagorean theorem. So let us see it, then what it says. If it is not that, then what it says? The next shloka, the earlier shloka was shloka number 49. The next shloka is shloka number 50. It says if we have uh, squares, uh, if we have to generate a square whose area is equal to the sum of two unequal squares. So let me explain it by the example. Look at the figure 1. We have two squares which are of different sides. Then what you will do, you will generate another square whose area will be the sum of the area of these two squares, the red square and the purple square. If you add their area, that should be the area of another square. Now, how you will do that? This it describes how to do that. So, what you will do is from the larger square, you take a portion in the along its length, which is same as the smaller square. So you look at figure 2, where we have drawn a p- purple rectangle in the larger square. The width of this rectangle length is the length of the larger square, width of the purple rectangle is the length of the smaller square. Now what we'll do is that next step 3 is draw the corner, hypotenuse or corner of the the rectangle, purple rectangle, draw that corner. Then in the fourth step, you extend the top side of the small square towards the rectangle. So that meets at this point. Then in the fifth stage, draw the corner of this lower rectangle. Now if you look at these two rectangles, purple rectangles, they are same size. Their size is same, length and width are same. Now the length of this rectangle, the purple rectangle is the length of the larger square, and the width of the purple rectangle is the length of the smaller square, and then the square is The third square is drawn, which is the dash square, whose side is the corner of this larger square and smaller square added, or the purple rectangle. Now, purple rectangle gives the corner of the purple rectangle gives us a square whose area is equal to the sum of the larger square and smaller square. What principle is used here? The length of the purple rectangle and the width of the purple rectangle, their squares are used and they produce the corner square, which was the previous slope. So therefore, it gives Bodhayana Sloka gives us the uh, Pythagoras theorem. Next. Then Manava Sloka, it gives us the Pythagoras theorem exactly. H is equal to square root of p square plus b square. Now, square root was not possible in those days in 570 BC to 490 BC in the Europe. They didn't know how to find out square root. So it was not possible for Pythagoras or the Egyptian or Arabs to find out this, to propose something like this. This was proposed purely in India, the Pythagoras theorem. Next. Now, some of the triplets that we found out in which are related to Pythagoras theorem are 3, 4, 5, 5, 12, 13, etc. These are listed here. What is interesting to note that these triplets, they follow the general rule which was stated above, which is h is equal to square root of p square plus b square. Next. Now, how do you get this? So this comes from the Katyayana Sutra. This is an identity. P a square is equal to p plus 1 by 2 whole square a square minus p minus 1 by 2 whole square a square. Now take p as q square and a as 1. So that becomes q square plus q square minus 1 by 2 whole square is equal to q square plus 1 by 2 whole square. Now if you take values of q as 3, 5, 7, if you take it as 3, then you will get the triplet 3, 4, 5. Take is as 5, you will get 5, 12, 13, etc. Now, this also can be presented in another form. So this equation, q square, the top q equation can be rewritten as 2q square plus q square minus 1 whole square is equal to q square plus 1 whole square. So if you do that, then for q, take 2, 4, 6, that will give us the same triplets. Next. Then how to generate other triplets? So the upper number, Silva Sutra, that involved the principle that if x, y, z satisfies the relation x square plus y square is z square, then px, py, pz also satisfies the same relation, where p is any arbitrary rational number. Using this from 3, 4, 5, you can generate 12, 16, 20 or 15, 20, 25. Similarly, from 5, 12, 13, you can generate 15, 36, 39, etc. So this is the principle in which triplets were generated in India. Next. We don't know whether these principles have been transmitted to other parts of the world or not. Now, using these principles, let us try to find out a square whose area is equal to sum of n equal squares, smaller square, take n smaller squares, which are of same area, then what will be their sum of area will be the area of another squares. So what you will do is, if there are n, this will be p, and not n equal square, this will be p equal squares. Now if you have p equal squares, then what you will do is, first draw a triangle. The base of the triangle is p minus 1, and the other sides, the triangle ABC. So BC is p minus 1 and BAC is p plus 1, which means BA is equal to p plus 1 by 2, AC is p plus 1 by 2. So if that is done, then BA we know, BD is equal to P minus 1 by 2. So BA, BD we know, therefore AD is equal to root PA. Now what is P? P is the total number of squares So for the square that we want to draw, its area will be root p square p a square. So it is AD is root pa square it, that gives us pa square. So this is how you will draw a square whose area is same as the sum of p equals smaller squares. Next. So with that we come to the recent era. In 1881, in a place called Baksali, near Pakistan, Peshawar, a farmer found some manuscripts, uh, big bark manuscripts he found. Those manuscripts, they were mathematical compendium of 70 folios, and now they are available at Bodleian libraries in Oxford. You cannot see them. We Indians cannot see them. We have to pay and see it from a distance. We cannot touch it, we cannot see. Now, these are Bitmark manuscripts. They are written in Gatha dialect of Prakriti and they use the Sarada scripts. They have been deciphered. Now, these barks have been carbon dated, and using carbon dating, people have found that these are the folio number 6. There are 70 folios. So 16th folio is dated to 224 to 383 current era. 17th folio is 680 to 868 current era. 33rd folio is 885 to 993 current era. So these are much before the Greek invaded India. At least that much we understand. Next. Then we know that zero was invented in India. Many people agree to this. And the first, for the earliest inscription of zero, modern zero, is dated to 875 CE. It is available in the Chaturbhuja temple in Gwalior. You can see this. I have shown this, highlighted that, and shown this. This is in the Nagari script, and there is no ambiguity. Everybody agrees to this, whether one is for supporting the West or whether one is supporting India. All are agreeing to this date and this uh, date of the zero. Uh, zero is available before that on the copper plates, but that those are contested by people who support European um, uh, European opinion. They say that this may be plagiarized like things. Okay, next. Now, if you look at the Bakshali manuscript, you can see a bold dot. That bold dot is the oldest record of zero. In the Bakshali manuscript, zero is represented by a bold dot. And Bakshali manuscript is how old it is, around 200 CE. So it is much before the go back. It is much before the Chaturbhuja temple, which is in 875 CE. Bakshali manuscript is 200 CE. So zero was available in India and was in use in India much before this time, 875 CE, much before 875 CE, zero was in use in India. Next. Now this gives the evidence of zero. This is a portion of the Bakshali manuscript which shows the multiplication of these two. Long multiplication procedure which includes zero is shown here. All these dots that you see in the manuscript, those are zeros. This has been deciphered and this multiplication so gives us this. Next, the evidence of zero. Now, the Bakshali manuscript also gives us a method of finding square root of a non-square number. Square number you can find out easily, but in those days, finding the square root of a non-square number is given like this. Suppose R is a non-square number, express it as the sum of a perfect square, largest perfect square plus some remainder. So R is equal to n square plus R. Then the zeroth approximation is square root of r, which is square root of n square plus r, that is approximately n. First approximation is root over of n square plus r, which is approximately equal to n plus r by 2n. Second approximation is root over of r is equal to n square plus r, that is approximately equal to n plus r by 2n minus r by 2n whole square divided by 2 times n plus r by 2n. Using this, we can find out root over of 5, which is correct up to 4 decimal points, 2.2361. Now you can use modern methods to verify that whether this is correct or not. One method is r is equal to n square plus r, so that you write as n into n plus 2r by 2n. Again, rewrite is add into this minus r by 2n and add it r by 2n. So multiply this. So then and that will be n plus r by 2n whole square minus r by 2n whole square. R by 2n will be a small number, its square will be much smaller, neglect that. So that gives us n plus r by 2n whole square. So r is root over of r is n plus r by 2n. So that is the first approximation. Similarly, for the second approximation, take the first approximation plus an error term. There is an error term. Then our square both the sides, n square plus r is equal to n plus r by 2n plus e whole square. Then do some algebra and neglect e square term. So if you do that, then you will find out e is approximately equal to r by 2n into minus r by 2n by 2 into n plus r by 2n. Therefore, root over of r is equal to n plus r by 2n minus r by 2n divided by 2 into n plus r by 2n. So using modern methods, you can prove that this is correct. What is given in Vaksari manuscript is correct. The error part is correct. Now, how did they came out with this? That is a question. How can, in those days, how can they come out with this? Modern days, let us see next. So let x square is equal to n square plus r. Then we'll write fx is equal to x square minus n square minus r. Then we know Newton-Raphson formula. Xi plus 1 is equal to xi minus fx by f dash xi. Once we know, if a function is given a function, you can find out its root using this Newton-Raphson formula. So zeroth approximation, let us take x is approximately equal to x0 is n. First approximation, I is equal to 0. So x1, that will be x0 minus fx0 by f dash x0. That will be n minus r by 2n, which is n plus r by 2n. That is the first approximation of Boxer manuscript. Second correction, I is equal to 1. So x2 is equal to x1 minus fx1 by f dash x1. So put those values, n plus r by 2n minus n plus r by 2n whole square minus n square minus r divided by 2 times n plus r by 2n. By 2n whole square divided by 2n plus r by 2n. Exactly same as given in the Vaksali manuscript or Vaksali formula. We don't know whether they knew the Newton-Raphson formula for deriving this or not, but this gives us this formula. Next. Now, every formula that is given in Vaksali manuscript is followed by an example. Let us take an example. Find the solution for 3 by 4x square plus 3 by 4x is equal to 7,000. Now, if you solve this, this is in the form of ax square plus bx is equal to c. So, x is equal to minus 3 plus 336009 root over by 6. So, we have to find out the square root of 336009. Now, that is r. That is our r. 336009 square root is r. So, r is equal to 336009. That is 579 square plus 768. Zeroth approximation is 579. First approximation is 579 plus 768 by 1158. Second approximation is approximately equal to 579.6628 up to this 841. So correct up to 13 digits. Now, once they solve this, they also use to verify whether the solution is correct or not. So what they do is they took this value uh, R2 as X and put it in the formula that was given to be solved. So in the first formula, 3 by 4 x square plus 3 by 4 x, that formula. If they put that in that formula, they find a numerator. For the left hand side, they find a numerator which is this big 50. It starts with 50, ends with 36. Denominator is 72, starts with 72 and ends with 6 zeros. Now look at the Boxari manuscript in the top. There are two numbers which are decoded using those scripts. They give exactly those numbers. And the ratio of those two numbers is exactly 7,000, which is the RHS. So they verified, and this is also verified that Boxari manuscript is correct. What they are doing is correct. Next. Then we know something called linear programming, which came after the Second World War. US military, they wanted to move men and material using the minimum cost. For that, George Danchis, he invented the simplex method of solving the linear programming in 1947. But it was very slow, exponential in low worst case, very slow, the LP. Then Narendra Karmakar, while working at AT&T Bell Laboratory, he developed an algorithm which is called Karmakara's algorithm. And Karmakara is listed as a highly cited researcher in the Institute for Scientific Information. And this Karmakara's algorithm was very fast compared to the LP programming algorithm. So this is a contribution from India. Let us see something else next. We'll see a problem from the Vatsal manuscript. The problem is one person possesses seven Asava horses, another has nine Haya horses, and another has 10 camels. Each gives two animals, one to each other, each of the others. They are then equally well off. Find the price of each animal and the total value of the animals possessed by each person. Now, this is perhaps the first LP problem of the world because LP problem is maximize C transpose X such that AX is equal to B. Now, this problem can be posed as 5x1 plus x2 plus x3 minus k is equal to 0. For in this, x1 is Asava versus x2 is say Haya versus x3 is say the camels. So the 5x1 plus x2 plus x3 minus k is equal to 0. x1 plus 7x2 plus x3 minus k is equal to 0. x1 plus x2 plus 8x3 minus k is equal to 0. Now what we have to do from this? We have to maximize 5, 1, 1 transpose x such that 4x1 minus 6x2 is equal to 0, 4x1 minus 7x3 is equal to 0. How do you get this? 4x1 minus 6x2. Subtract the second equation from the first equation. Similarly, 4x1 minus 7x3. Subtract the third equation from the first equation. So this is the constraint. And the other constraint is x1, x2, x3 are to be integers. So this is what is to be done. This is done in the Vaksali manuscript. This next. This problem is solved in the Vaksali manuscript with k is equal to 262, taking k is equal to 262, this is x1 is equal to 42, x2 is equal to 28, x3 is equal to 24. But actually this can be solved using for smallest value of k, which is 131. There we will get x1 21, x2 14, and x3 12. But why they have taken 40, a k is equal to 622? Maybe the reason is that the price. So at that time, whatever was the price of these horses or camels, taking that price into consideration, they have made this. So that can be the order. And they have solved this Bakshali manuscript. In the Bakshali manuscript, the complete solution is given there. I am giving you the solved values here only. So that gives us the solution, Bakshali manuscript solution to this problem. Both these k values, K262 with 131, they satisfy this constraint equation. So with that, I will stop for today. We'll have discussions. If you have any questions or if you have any comments, I'll be very happy to take them, and we'll continue next time on the Monday.
Uh,
So the
uh,
session is now open to questions.
Hello, hello. Can you hear me?
Yes, sir.
Yes,
I
you
can
are
hear.
audible.
Okay, I am Dr. Raghavan from NIT Trichy, 70
Sir.
years old. Morning, I gave a lecture to another university of Bhubaneswar, and I mentioned one sentence that Rabindra K. Mishra is a god in certain things. That time, I did not realize and told. But now, after hearing this wonderful, unique lecture in my life, I really feel he's God. I do not know how and when he shifted from electronics, mathematics like MDTD to this side. I hope, I think he should get one more PhD on this topic. I don't have any more words. I am sure that Dr. PK Sahu also will support me. And
Yeah, yeah, definitely. I am also seconding you as part of this committee. So I second you.
thank you, sir. Thank you, sir. Next time for the second meeting, with the help of Dr. P.K. Basu, I will bring another stalwart, 82 years old, Dr. B.N. Basu, also to hear this wonderful lecture.
Thank you,
Okay.
sir, so much.
Thank you.
Thank you.
Great,
I
great.
shall try to invite my friend Buddhi Bosu as well as my classmate is Anantha Krishnan, who might be interested, who is the vice president of INSA. And okay, let's see whether they find time to join. But while I repeat my previous suggestion made to Professor Misra that uh, in at any cost, this research must be, I mean, put in a book form or must be published in some way or other. So
Sir,
I
I am
think,
trying to work on that. I have started writing something,
mm,
but hopefully I will complete the book in about 6 months to 1 year.
oh,
Hopefully I'll do
that's
that.
very nice, very nice.
Thank you, sir.
Certainly. Great, great.
In
Yes,
the rebirth of Dr. Mishra, God has given him some extra brain power, I think.
certainly.
Uh, sir,
I
I
just have
cannot
one
go to
comment,
that.
Professor
Sir,
Misra.
sir,
I have
sir.
one comment.
Yes,
In
sir.
some of the slides you read, you wrote Baksali, Baksh,
Bhaktali.
and
Yes,
in the next slide you wrote Bhakshali, Vhak. So
actually it is
I think it
Bhaktali.
should be
Yes,
must be
yes.
uniform,
Sir,
right?
it is Bhaktali. Yes,
Mm.
yes, yes.
Mm.
It is Bhaktali. BH.
So, so any other questions, queries, or comments from the audience? Any other?
Hello, sir. Good evening.
Yeah,
Good
yes.
evening.
Yeah, actually, I wrote my question in the comment. I am Dr. Sambhudatta from VIT University.
From which
Good afternoon,
university?
sir. VIT Belur Institute of Technology, Andhra Pradesh.
Andhra Pradesh. Okay, fine. Please.
Uh, Good afternoon, sir. It was a very insightful and very technically very good talk. Thank you for that. I was going through all the slides in the YouTube live as well because I joined little late. So in the last slide, I had one doubt there. So X1, X2, X3, then we'll speak about the prices and what the K talks about. It's a constant, it's okay. But the
Mhm.
question says that what is the price of each animal? So X1, X2, X3, we understood. I understood. What is the
Right,
significance of K there? What does that
right,
signify
right,
there?
right, right. After they gave one animal to each other, the value of the animal became same with each one. So suppose the first one has 6 horse, 10 camels, then price of 6 horse and 10 camel is K. Second one has 5 horse, 11 camels. So price of that is K. So K is their
Okay,
constant,
okay,
the total
okay,
price of
okay,
that.
okay, got it. Anyway, sir, thank you for choosing this topic where nobody talks about, and it's really great to listen these topics. Thank you, sir.
Thank you. Hopefully, we'll attend the next uh, one Monday. On Monday,
Yeah,
I will
yes,
talk
sir.
about trigonometry, etc. Thank you.
Surely, sir.
So there are no further queries. It is my customary duty to once again express Ravindra Mishra for giving this very elaborate tips and very detailed explorations of the sound mathematical systems that was early back developed in Indian educations long back ago. So we are really unaware of this particular knowledge, and I believe the success of this faculty development program, if the lighter of these points be carried out to young researchers and other faculties, so they may be motivated to carry down their works in the same line as what Professor Mishra has highlighted and gave us the pointers. So I also take this opportunity to thanks Professor PK Vasu, because he gave me the source of inviting Professor Ravindra Mishra in one conference we met together, and PKB sir just gave us the suggestions that why not you are inviting Professor Ravindran Mishras. Okay, so he took the pain of inviting Professor Mishras, and this is a really a very good opportunity to interact with all these illuminary persons like Professor Mishra, Professor Basus, etc. And that would be the real success of this particular FDP, where we are having this interactions of so many luminaries. So I believe that with this, we conclude today's sessions. And so happy weekend for all of you. We'll again meet on Monday, and we'll have more certain distinguished speakers in these areas. So for the time beings, thanks to all of you. Thank you.
Thank you. Nitin.